Welcome to This Explainer. I am so incredibly thrilled you're here today because we're jumping right into a totally mind-blowing journey. Today, we are going to bridge two completely different worlds. We're going to start with this intimately touching, deeply personal tale of human endurance and just endless waiting. And from there, we're going to zoom way, way out to look at the tiny, ancient biological forces, these microscopic vectors that have literally shaped human history. We're talking about pests that have toppled entire armies and are right now adapting to our rapidly changing climate. It's a story of resilience in both its most beautiful and, honestly, its most terrifying forms. To really wrap our heads around this kind of resilience, let's start with a deeply personal story. This is Sirchis Kaplan, but most people knew him as Amma Bahe. Bahe spent 7 remarkable decades, 70 years, living and waiting at the Deyurulzaforen Monastery in Mardin, Turkey. Just pause and think about that for a second. 70 years in one single place, with his eyes constantly fixed on the monastery's gates, waiting for someone who is never going to return. So, who was he waiting for? His mother. When Baha'i was just a 6-year-old boy, his mother, who was widowed and struggling in profound poverty with 4 kids, had to make the heartbreaking decision to migrate to Syria. But Baha'i was fragile. He carried physical and mental trauma from a really severe childhood injury. Fearing he just wouldn't survive the journey, his mother left him in the care of the monastery. And as she walked out the door, she made a promise to her 6-year-old boy. "Stay here, I will return." That simple, completely devastating promise turned Baha'i into a permanent, deeply beloved fixture of the monastery. The locals actually gave Baha'i a beautiful nickname, Binebil. In Syriac, that translates to nightingale, or bulbul, which also happened to be the name of his birth village. Now, in the rich culture of Mardin, the nightingale is this profound symbol of deep longing, a kind of beautiful but tragic melancholy. It literally perfectly mirrors Baha's own life of endless waiting, as well as his gentle innocence despite all that childhood trauma. When he passed away in 2014, the monastery didn't just mourn a man. They said it felt like they'd lost a foundational stone of the building itself. Okay, here is our roadmap for today. We'll start with the Nightingale of Mardin, then move to the evolution of ancient ectoparasites, vectors of historical epidemics, climate change and spillovers, and finally, the future of prevention. All right, part 2. Let's dive right into the incredible evolution of ancient ectoparasites. The timeline on these little pests? Absolutely mind-blowing. We are talking about a kind of biological patience that spans millions of years. I mean, in fossil records from China dating all the way back to the Middle Jurassic and early Cretaceous periods, scientists have found perfectly preserved giant fleas. And get this, they were already equipped with tough, piercing, sucking mouthparts. Fast forward a few million years to ancient Egypt, and researchers found the dog tick, Rhipisophilus sanguineus, literally clinging to mummified dogs. So, long before these parasites were bothering us in our modern living rooms, they were surviving the collapse of entire empires and spreading all across Eurasia. Their real secret weapon is adaptability. Over 94% of known flea species specifically target mammalian hosts, creatures with warm blood and lots of fur. But in this crazy display of evolutionary gymnastics, a small fraction, about 3%, made the leap to avian hosts. Think back to the common nightingale we were just talking about, Lucinia megarhencos. It has some really specific biological traits. It has a complex song, it lives in dense thickets, and it takes these long migratory flight paths. All of that constant movement makes it a prime target. These tiny fleas crossed huge biological boundaries just to infest birds like the nightingale, finding a stable, moving environment to feed and survive on. Moving right along to Section 3, how these ancient survivors became vectors of historical epidemics. Geography and trade can easily turn a bustling city into an absolute epicenter of death. Take Varna, for example. It's a strategic port city on the Black Sea in modern-day Bulgaria. Because it was such a massive hub for international trade, merchants, and military movements in the 19th century, it tragically became a huge hotbed for historical epidemics. It's a perfect case study for how these things spread. Breaking down the specific outbreaks in Varna reveals a pretty terrifying pattern. You've got the plague, mostly driven by fleas, hitting Varna again and again, arriving on merchant ships straight across the Black Sea. Then there's typhus. Spread by human lice, typhus caused absolutely devastating casualties among soldiers and refugees during conflicts like the 1839 Ottoman-Egyptian War and World War I. But honestly, cholera during the Crimean War in 1854 might be the most horrifying. Fueled by poor hygiene and contaminated water, it ripped through French and British troops stationed in Varna, killing thousands of soldiers before they ever even saw a battlefield. I really want to emphasize this wild contrast. On one hand, you have the microscopic catalyst, a tiny infected flea, a tick, a single louse, right? And on the other hand, you have the macroscopic tragedy, entire armies collapsing, mass graves, bustling cities grinding to a halt. During the Crimean War, the disease death rate was so staggering that soldiers would be perfectly healthy at breakfast and dying in pure agony just hours later. It is a deeply sobering reminder of how nature's tiniest vectors can trigger our absolute largest catastrophes. Okay, Section 4, let's talk about climate change and zoonotic spillovers. Let's zero in on mosquitoes for a second, specifically Culex pipiens, the common house mosquito. Since the 1980s, industrialization and rising global temperatures have totally shifted the landscape. We're seeing major changes in abiotic conditions, meaning non-living factors like extreme heat and humidity, but also in biotic factors, like how densely packed the mosquito larvae are. In places like Antalya, this warming trend has literally hit the fast-forward button on their breeding cycles. They aren't just surviving, they are exploding in numbers, with annual generations jumping from 24 up to 28. And the hard data totally backs this up. Research points to a statistically significant increase in annual average temperatures of 0.038 degrees per year in that region. So what does this mean? It proves that climate change isn't just some abstract concept about things getting a bit warmer. It is an active, biological catalyst. We are literally handing disease vectors more opportunities to multiply, thrive, and potentially spill over into human populations. But hey, we don't need to look at tropical mosquitoes or 19th century battlefields to see this fight playing out. We are battling ancient vectors every single day. Just think about head lice. These little parasites are still thriving right now in crowded places like elementary schools, spreading like wildfire through close personal contact. It just goes to show that our coexistence with these microscopic hitchhikers is a very modern daily reality. And when these parasites interact with wildlife, things get even more dangerous through a process called co-feeding. Think back to the nightingale we discussed earlier, acting as this ecological host. Imagine several ticks, like Hyaloma marginatum, feeding really close together on that exact same bird. Even if the nightingale itself doesn't have a virus in its blood, a single infected tick can directly transmit a deadly pathogen, like the Crimean Congo hemorrhagic fever virus, straight to the uninfected ticks feeding right next to it. The bird unwittingly acts as an amplifier, turning a small localized infection into a widespread threat. It's honestly fascinating, but also pretty scary. Which brings us to our final section, the future of prevention. Here is the incredible news. Modern science is completely flipping the script. Instead of just trying to make vaccines for the diseases these bugs carry, scientists are now creating vaccines against the vectors themselves. It's genius. They've pinpointed the exact molecules a tick needs to survive. By targeting internal tick proteins, like ferritin-1 and ferritin-2, they can brilliantly disrupt the tick's ability to digest blood or process iron. So if a tick bites a vaccinated person or animal, it drinks in antibodies that basically act like a poison to its own system, stopping it from surviving or reproducing. It is an incredibly elegant, highly targeted defense. So let's pull all of this together. From a gentle young boy nicknamed the Nightingale quietly waiting at a monastery for 70 years, to giant fleas roaming around the Jurassic era, all the way to modern labs designing targeted tick vaccines, life is just this massive, incredible tapestry of endurance. We've seen how tiny bugs brought huge armies to their knees, and how a warming planet is supercharging them all over again. Which leaves us with a pretty vital question to ponder. If these tiny, incredibly patient parasites have so profoundly shaped our human past, how exactly will our changing climate shape the pandemics of our future? Thank you so much for joining me for this explainer, and as always, keep questioning the world around you.